asleep at 7:30.
I won't do that. This is too good. So when I derive or want to learn a new numerical method, the pattern that really worked for me was, of course, I would get all the literature on it, and the literature is usually very unreadable, right? But that's all I had to go on. I would open up Microsoft Word with Equation Editor and MATLAB, and I would start off with Maxwell's equations each time and derive every painful step all the way to the final equations that I would implement in MATLAB. Then I'd go to MATLAB and implement them, and of course it doesn't work, right? And so, then I go back to the formulation, the code, and you whittle at it until finally everything works. And when it works, that's cool. Now we have this complete, nice, detailed formulation, so we understand everything about the method, and it's working, and everything's wonderful. So that's my technique for doing this. So the pattern in this class, we're going to follow that. We're going to start at Maxwell's equations, and they're in its purest form, and go step by step for every single method. And what you'll see is it actually becomes repetitive and commonality. Oh, okay, yeah, I can do that. And I think by the end of this class, you'll be a lot less intimidated by Maxwell's equations. They can be intimidating at first. But what you're going to see is after a while, all these formulations are the same. And suddenly, there's going to be a new numerical method later on in your life, and you'll be all over because you'll know exactly what to do and how to whip the equations around because it's very repetitive. So the purpose of this lecture is, one, if your background does not include electromagnetics or Maxwell's equations, to talk about that a bit and try to give you a picture of what's going on there. And the pictures are going to be important because then when we implement it numerically, you're going to see it's consistent with those pictures. And that will also make more sense when we get to it. So we'll step through Maxwell's equations. We'll also, there's a section here that's probably the most important. It says preparing Maxwell's equations for computation. And there's some steps that we'll go through to get them ready to implement. And we'll have this final set of Maxwell's equations. And pretty much all the other methods, we're going to start there with that sort of prepared version of Maxwell. So everything's going to be normalized, all that kind of stuff. So that's the flow. So let's skip the outline. Of course, Maxwell, he did not invent Maxwell's equations. All he did was write them down. In fact, when he wrote them down, there were something like 27 equations or some ridiculously high number like that, 19, 20, somewhere like that. It was another guy named Heaviside that actually wrote them in the form that we know now. But Maxwell kind of gets the credit for it. I'm not sure why. They should be called Heaviside equations. All right, enough of that. So here they are in their full glory. I actually repeated them 4 different times here because there's integral form versus differential form, time domain versus frequency domain. So it's a little 4x4 matrix. So in this corner, you have the integral time domain form, differential time domain form, and down here, the differential frequency domain form. And these are what we're going to use most, the differential frequency. And notice they're the simplest. And so there's a good reason why people like frequency domain methods, because it's usually the simplest. And there's also frequency domain integral equations. Another thing to keep in mind, in addition to Maxwell's equations, there is these constitutive relations. But anyway, in one slide, there's all of Maxwell's equations, the parameters, their units, and all that. So you can print that out as a summary sheet or whatever. In addition to Maxwell's equations, there's a thing called Lorentz Force Law. We're not going to deal with that in this class, but it's there. So in addition to Maxwell's equations, you need this to describe all of classical electrodynamics. But in our codes, nothing's going to be moving, so we don't need these. If it was moving, we would need them. And there actually is a generalization to Maxwell's equations for moving media. It's actually kind of neat because if you have one material moving past the next and you have the electromagnetic wave, for example, jumping over into the other one, there's a Doppler shift. And it actually changes frequency. And so if it's changing frequency, it's changing energy, which means it's imparting momentum. So you can actually make things move with electromagnetic waves. We're not going to do that here, but wanted to point it out. So the first one is Gauss's law. And what's kind of neat, you'll notice that there's 4 Maxwell's equations, and you'll see that we really tend to only use the curl equations. But we still need to enforce these dot equations, but we're going to do it in a strange way. That'll become clear when we get to it. But we do need to understand them. So what Gauss's law says, if you have a charge, the field lines diverge from it. And that's really all it says. There's an integral form of that which says, okay, so if you wrap a surface around that charge and you add up all the fields sticking out of it, you can figure out how much charge was there to begin with. So that's Gauss's law. And this also says if this charge term is 0, that the D field forms loops. So it becomes solenoidal at that point. And for everything we're going to model, there will be no charge. That's mostly an electrostatics kind of thing. So our fields are going to form loops. There is an equivalent Gauss's law for magnetism, and there is no such thing as magnetic charge. Although there is something called spin ice, which is actually getting some attention recently. It was invented a time ago, but supposedly there's magnetic charges, like positive and negative magnetic charges. And so that would be non-zero there, and the stuff called spin ice. I don't know a lot about it. I'm just mentioning it if you want to go pursue that. But anyway, so no magnetic charge in here, no magnetic monopole. So the magnetic fields always form loops. Until there is magnetic charge, it will always form loops. So when we're talking about waves, there are some consequences of not having divergence. So there's no charges, so the divergence equation equals 0. Del dot the field equals 0. That means that the D and the B fields will be perpendicular to the direction the wave is going. And we'll need to know this kind of thing when we set up sources for our models. But that's the big consequence of the divergence equations. The D and B is perpendicular to the direction the wave is going. Okay, on to one of the big ones now. So we got Ampere's law, sometimes called Ampere's law with Maxwell's correction. And what this says is, I'll stand up for this. So del cross H, this is a curl, right? So it's saying if the magnetic field is in any way doing circles, at the center of that, there either has to be a current or a time-changing electric field. And we all know if we have a wire and there's current passing down it, we get a magnetic field around it. This is also bidirectional. So if you force current down the wire, you will cause an circulating magnetic field. Or if you had a wire without current and you forced a circulating magnetic field around it, it would force a current. If there was no wire there and you forced the circulating magnetic field, it would induce a D field there at the center of the circulation. And in fact, it doesn't even have to do loops. All it has to do is turn a little bit, and that's kind of a rotation. It's going to induce a little electric field there. So that's Ampere's circuit law. An equivalent one, the handedness changes because of the minus sign there, but it says if you have a circulating electric field, if you could somehow force that, it's going to induce a B field at the center of that circulation. Or likewise, if I could take the B field and start changing it, it would induce a circulating electric field. But these two pictures of E fields circling H fields is going to come up again when we get to finite differences, because it's going to be unstable until we fix it. And the fix is we're actually going to make it much more consistent with this picture here. E fields wrapping around H fields wrapping around electric fields. So, and you'll see these pictures again when we start approximating Maxwell's equations with finite differences, because we're actually going to write our finite differences consistent with these pictures. And that's why everything's going to work. Anyway, that's called Faraday's law of induction. So the consequence of the curl equations, it's commonly said Maxwell's equations predict waves. And it's because of the curl equations. If we have a time-changing electric field, which then produces a time-changing magnetic field, Then the time-changing magnetic field induces another time-changing electric field, and that just keeps going, and we get waves. And so the way I envision this, I don't know if it's a great way, but we'll start off with a magnetic field here, and somehow we force this magnetic field to be changing. Well, that's changing in a straight line. That's going to induce a circulating electric field. That's also changing in time, so it's going back and forth like that. So we'll just draw one ring. So now we look at an electric field here, just at this point. It is changing everywhere, but we'll just look at one point. But now we have an electric field that's changing in and out of the board here. Well, that's going to induce a circulating magnetic field, which is now changing in time. So if I look at the magnetic field here, it's now changing up and down. There's going to be an circulating electric field around it, and that just keeps going. And in fact, the radiation is going to go in more directions. So Maxwell's equations predict waves, and that's how I envision it. And the way we implement some of the numerical methods is going to be very consistent with that. Any questions on that? Okay, so notice, I almost went back, I stopped myself. Notice Maxwell's equations didn't have any materials in them, right? So you guys could win money in a bar bet with an electromagnetics person saying, Maxwell's equations doesn't tell you how waves interact with materials. That's absolutely true. There's no materials in those equations. So it more just answers what causes fields. There's two additional equations that we need called the Constitutive Relations. And one of them is the D field times the E field, but the proportionality constant here is this epsilon. That's sometimes called dielectric constant. It's the permittivity, sometimes it's called. And it's a measure of how much the electric fields interact with the material. The bigger that number, the more interaction there's going to be, and the more we can control the wave. But D and E are not two separate phenomena. They're actually the same phenomenon, just there's a slightly different interpretation, and I don't think I get into it here, but here's the short story. In a material, you have electrons buzzing around the nucleus, right? So when an electromagnetic wave is passing through that, now you have an electric field and charges, and that puts a force on the charges. It pushes the nucleuses one way, nuclei, and these little electron clouds the other way. The electron cloud's stuck. It's not going to pop off unless you push it really hard. But in the presence of the electric field, it stretches those things. And now that you have this stretched little dipole now, that's actually storing a little bit of your electric energy. And then when it springs back, it releases that, and it releases it out of phase, so it combines with the applied wave out of phase, and you get this overall slowing effect, especially when you average it over trillions and trillions of atoms. So this permittivity term is really a measure of the material's ability to stretch in the presence of an electric field. D and E are not separate phenomena. E is kind of like the initial push. That displaces charges, combines with the applied E, and so the overall effect of the electric fields and stretched little dipoles is D. Sometimes they call it the displacement field because it's accounting for the displaced atoms. There's a thing called dispersion, and this is where that dielectric constant changes with frequency, and that happens all the time. The dielectric constant's never the same with frequency. There are some places where it's pretty flat, but it always changes with frequency. So in fact, in the time domain, it's actually a convolution. It's not a multiplication. So that leads to wonderful problems when you model things in the time domain and want to account for dispersion. But in the frequency domain, what happens when we Fourier transform a convolution? It just becomes multiplication, and it's brainless at that point. So another reason why we like modeling things in the frequency domain. Another thing we could talk about is anisotropic materials. So imagine you have a material where the electric field's oscillating this way, and maybe it sees a dielectric constant of 2. Then if it's oscillating this way, it might see a dielectric constant of 3. Or this way, it might see a dielectric constant of 6. If it changes with which way the field's oscillating, That's called an anisotropic material. We're not going to do anything with anisotropic materials in this class because it really kind of jumbles up the game and complicates things. But there are some very interesting things that can happen inside anisotropic materials. We're doing a lot with that now. In fact, we're pioneering some really cool things at UTEP. One thing we found, if you take a transmission line, right, it has this little electric field around it that's kind of like a cloud. If you embed that in something that's anisotropic, so it's a different dielectric constant, different directions, the field, this cloud around the transmission line, tends to get pulled in the direction with the highest dielectric constant. So what we'll do is we can design our own materials that have our own anisotropy where only one direction has a high dielectric constant, the other two are low. So it only gets pulled in one direction. And then we can start spatially varying that so the field around the device becomes like clay and we can sculpt it. And so we're using these anisotropic materials to do that. But anyway, once things are anisotropic, this epsilon becomes a tensor. It's a 3x3 matrix. And so in that case, the D field and the E field are not pointing in the same direction anymore because this tensor modifies that. Another generalization to this is this dielectric constant can be nonlinear. In fact, everything's nonlinear, which means if you drive it with a more intense electric field, it actually changes. So the properties of the material change depending on how intense or strong the electromagnetic field is. And all kinds of crazy things happen there. Now, we're not going to do that in this class either, but some neat things happen. You can get frequency doubling. You can get rectification, where you throw one frequency in and it actually gives you a static field. The frequency doubling is used a lot in lasers. Like sometimes if we can't figure out a medium that lasers at a particular color, we'll get something that lasers at another color and send it through a frequency doubling crystal. And that happens a lot. So I have a yellow laser pointer, and that has like 3 different stages in it, where you have this first lasing stage, and then there's doubling stages after that. It's all packed into a little laser pointer. So it's just this top simple case that we're going to do in this class, where this epsilon is a scalar, just a single number, and we can model a heck of a lot of things with that. And I think I can leave you at the point where if you ever come across something that's anisotropic or nonlinear, you have a pretty good idea of how to get started to do that. All together now. So we have Maxwell's equations up top, and the way I would describe it is that answers what produces fields. So time-changing H's cause time-changing E's, and so on. And the constitutive relations describe how the fields interact with the materials. And so it's the combination of the two that describes everything. Everybody good with that? Okay.
So
I can't go back.
Then the permeability will be vector first?
The permittivity is not a vector. It's just going to be a scalar number, a single number. If it's a tensor, it's a 3x3 matrix of scalar numbers. It's not a vector. The only thing that are vectors here are the fields, the electric and magnetic fields. And we have 4. We have the D field and the E field, the B field and the H field. And they're all vectors. Okay, physical boundary conditions. Skipping the derivation of this, the end result is the tangential components of E and H are continuous across the interface. So that's these guys. But only the E and H fields. That does not hold for D and B. In fact, for D and B, it's the normal components that are continuous across the interface. What you're going to see in our codes, we're going to eliminate D and B and only retain E and H. We're going to substitute equations around, and in just a little bit we'll do that. And so that's why I'm not showing the boundary conditions for D and B. So tangential components of E and H are continuous across the interface. And we can't say that about the normal components. Those are discontinuous across the interface. But one thing that's kind of cool is that the product of the dielectric constant on one side times the normal component of E, that product is continuous across the interface. And that'll crop up later, and you see that's going to save us to fix some things about some methods that would otherwise be inefficient or converge slowly. So tangential component's continuous. The normal components are only continuous when you multiply by the material properties. So the product of epsilon times the normal component of E, that product is continuous. Or also the permeability mu times the normal component of H. That product is also continuous across the interface. We're going to describe waves with a wave vector. So it's a vector pointing in the direction the wave is moving. We're going to call that K. The tangential component of that is also continuous across the interface. So we're rarely going to use this normal component thing. So everything else, just remember tangential components, continuous across the interface. And that's what we're going to use 99% of the time. Okay. Parameter relations. There's a lot of different parameters. We can talk about wave vectors, attenuation coefficient, loss tangent, dielectric constant. It gets very confusing. So I gave you guys a map to sort it all out. If you get confused, just refer to this. Clear it right up. Okay. So the first thing we come to is the permittivity. And so I just described it from a very materials-related perspective. There's another way to think about it. If we substitute the constitutive relations into the curl equations, we'll end up with an equation with just H and E, with epsilon in there. So another way to think about the permittivity is if we have a circulating H, it's going to induce a time-changing E field where the dielectric constant is the constant of proportionality. How much E field does it induce? Well, that depends on your epsilon. The bigger the epsilon, I guess the smaller the field it will induce. Also in the frequency domain, something to keep in mind is that this permittivity is actually a complex number. It has a real and an imaginary part. That's not the case when you're in the time domain. But we're not going to do any time domain codes here. We're going to do a frequency domain, and it's complex. The imaginary term comes up when there's loss. And a lot of times we're just going to ignore loss in this class. We're going to formulate our code so you can just put it in as a complex dielectric constant, and you can account for loss, but for the most part we're going to model things without loss. So that's the permittivity. We can write permittivity as a product of the permittivity of free space times a unitless constant. And this constant is what we actually call the dielectric constant. And rarely do I talk about permittivity. I usually just talk about the dielectric constant. And it's implied that when you stick that in Maxwell's equations, you got to multiply by this free space permittivity, which is 8.854 times 10 to the minus 12 farads per meter. And because that's ugly and has ugly units, that's why we like to talk about dielectric constant. It's no unit, it's just something like 2. A lot of plastics have a dielectric constant like 2.5. Some of the higher dielectric constants we use are like 10 to 20. And inside capacitors, it can be many thousands for dielectric constant. Relative permeability, this is the same exact thing, but it's the other curl equation now. We substitute constitutive relations into the curl equations, and we end up here. And again, now the permeability is another proportionality constant. If we have a circulating electric field, it induces a magnetic field at the center of the circulation. And how much does it produce? Well, the permeability is that constant of proportionality. And it's the magnetic response of the material. But just like the permittivity, it has a real and an imaginary part. And we can also talk about the relative permeability, which is a unitless number. And for the same reasons, it's the actual permeability itself has ugly units and scale. So we just talk about this relative permeability. And for the most part in this class, we're just going to assume that that permeability is 1, meaning the material doesn't have a magnetic response. We're going to formulate all the codes with it in there so you can play with it. But for the most part, we're going to just set that to 1 and only deal with dielectric materials, which is the most common thing. But there are some cool things that can happen with the magnetics in there. Okay, there's sort of 2 worlds where we can specify material properties. We know we have a dielectric constant, we have loss. We can lump that into a complex dielectric constant, or in another school of thought, we want a purely real dielectric constant and a conductivity. But notice in each case there's 2 numbers. You either have a real and imaginary part of a complex number, or you have a real permittivity and a real conductivity. So it's kind of like conservation of information, two numbers describing. And I have seen systems that have a complex dielectric constant and a conductivity, and in my mind that's kind of crazy because there's redundant information happening there, and I don't even know what that means. So in this class we're only either going to use a complex permittivity or a real permittivity and a conductivity. And my favorite is just to stick with a complex permittivity because that's just one less number you got to put into your models. So we can write this Maxwell's curl equation this way, where del cross H equals j omega epsilon times E, but I'm putting in the complex dielectric constant. Or we can write del cross H equals, this was J, the current, but it's also conductivity times E plus j omega E. And so if I equate these sides, I can actually derive some equations to convert from one system to the other. So I think in this class, are just going to use the complex permittivity, but if you ever are reading somewhere they're using the other system, you'll know how to get your complex permittivity then. Is that good? Everybody good? Refractive index. So the permittivity and permeability, they appear in Maxwell's equations. So I would word it that they're the most fundamental parameters in Maxwell's equations. They're the ones we want to come up with to model something. However, they're not, in my opinion, they're not very intuitive numbers. You can't tell me the dielectric constant and permeability and give me a feel of what's going on. So refractive index is a parameter that's less fundamental to Maxwell's equations, but is more physically tangible. You can actually get some physical meaning out of that. And refractive index is kind of like a density. It's how much the wave slows down. So if the speed inside a material is half what it is in a vacuum, refractive index is 2. If it's a third what it is in a vacuum, the refractive index is 3. So it tells you how much the wave slows down. Well, interestingly, if the permittivity and permeability can be complex numbers, so can the refractive index. So what on earth does that mean? So we have a real and an imaginary part. And this is kind of cool, and this is why this is very physically useful. The real part of refractive index tells you everything about how fast the wave is traveling. Everything's isolated there. The imaginary part tells you how quickly it decays, because it's getting absorbed, right? Because there's loss. And those are two very separate parameters, and K does not affect N at all, and N does not affect K. Whereas if we were to go back to the complex permittivity, it's not clear, given real and imaginary numbers, what's happening. It's not clear how fast it decays. It's not clear how quickly the wave would propagate. But given refractive index, the real part is how fast the wave goes, and the imaginary part is how quickly it decays. So it's a much more physical parameter in my mind. And the imaginary part, that kappa, is called the extinction coefficient. We'll have what's called a propagation constant. So we got a wave, and it's trucking along. And so we characterize the propagation amplitude. This is the propagation term, e to the minus gamma z. So gamma has two things going on then. It has how quickly the wave is traveling, how quickly it's accumulating phase, but also its decay. So gamma is a complex number to convey those two pieces of things. So gamma has a real and an imaginary part. So if I take alpha plus j beta, I'll point to it on here. If I take this alpha and j beta and substitute that in up here, what I'll get is the electric field is e to the minus alpha z times e to the minus j beta z. Clearly this is a decay term. So the real part of gamma is responsible exclusively for decay, and the imaginary part of gamma is responsible exclusively for propagation. It's a complex exponential, so that's a sine cosine thing, so it's a wave that's traveling. And we can relate this propagation constant to the refractive index through this equation. We just multiply it by k naught, which is called the free space wave number, and the free space wave number is 2 pi divided by the wavelength. And I think that'll be another slide too. we have the absorption coefficient. Now, unfortunately, we're using the symbol alpha twice, and even more unfortunately for a very similar thing, but they actually mean different things. The attenuation coefficient tells you how the amplitude of the wave decays. The absorption coefficient tells you how quickly the power decays, which is the squared version of amplitude. And unfortunately, alpha is used twice for both, and I wish I could reconcile that for you. So at least in the next few slides, I'm going to have alpha sub ABS to be the absorption coefficient. That's the power-related one. And then here's the absorption coefficient, the attenuation coefficient. And they're just different by a magnitude of 2 because power is the amplitude squared, right? So there's a 2 in there. And the absorption coefficient is related to the extinction coefficient. They're almost the same parameter, just a constant different. Then there's loss tangent. You won't see me use this much, but this is kind of a historical thing that's used a lot more in microwaves. In the optics world, they talk about refractive index. In microwaves, they talk about dielectric constant and loss tangent. It's called a loss tangent because you can make a triangle out of your material properties and there's an angle delta. That's not important. What is important, again, that the loss tangent is sort of like the extinction coefficient and the absorption coefficient. It's exclusively a loss term. So whereas I mentioned before, the dielectric constant has a real and imaginary part, but it's not clear what the loss is just given those two numbers. Well, loss tangent, that's one number that completely characterizes the loss. So to give you an idea of some typical loss tangents, a really high performance dielectric that doesn't have much loss is like 0.0001 loss tangent. Some of the crappier materials we're using in the 3D printing lab have loss tangents like 0.1, 0.2, and that's pretty lossy. It's still somewhat usable, but just give you an idea of the numbers. So we're not really going to use loss tangent in this class, but I want you familiar with the word, and now you have the equations given that to calculate absorption coefficient, which is something that we would use. Material impedance. The impedance just tells you the ratio between E and H, so it just prescribes a balance between the electric and magnetic fields. The real important thing here is that the ratio of E over H is the impedance. The impedance of free space is like 376 ohms. So that tells us that E and H are 3 orders of magnitude different. So there's a normalization thing that has to happen there. And we're going to multiply or divide one or the other by the free space impedance to get the two being equal magnitude. But anyway, so the impedance isn't really good or bad to have high or low. It just describes the balance between E and H. It doesn't tell you anything about the speed of the wave or the attenuation. It's just the balance between E and H. And it's also a complex number. Rather than look at it in terms of real and an imaginary, think of it in terms of a magnitude and a phase. The magnitude tells you the balance between E and H. The phase tells you the phase between E and H. H is a cosine, and E is a cosine, and they could be out of phase. So that's the angle part of impedance. We have omega versus F. Omega is the radial frequency, that's radians per second, as opposed to F, which is called the ordinary frequency, which is hertz, cycles per second. And they're different from each other by 2 pi. And I guess I use them essentially interchangeably, but they are not the same. There's a 2 pi difference between the two. So wavelength and frequency. Frequency is actually the more fundamental parameter because frequency doesn't change unless you're in a nonlinear material. We're not going to do that. But frequency doesn't change. That's the thing. No matter what's happening to the wave, it's at the same frequency always. But if it's in a material and slows down, the wavelength can change. So the wavelength actually changes depending what material the wave is in. But the frequency is constant. You can convert back and forth. The speed of the wave is the frequency times the wavelength. So if we're in outer space, then we have the speed of light equals frequency times the wavelength. And we can also get refractive index from this. When the wave enters a material, it slows down, travels slower. So since it slows down, the wavelength gets compressed. And so if we take the speed of light divided by the refractive index, that's actually the velocity of the wave. But so frequencies, that's the fundamental thing. The wavelength changes depending where it is. Everybody good with that? Sign conventions. I bring this up because this is intensely confusing if you're not aware that it's an issue. But I can choose to describe propagation as either e to the minus j beta z or e to the positive j beta z. And both can describe forward propagation in z. And it doesn't matter which you choose, they'll both work. It's just a convention. In physics and chemistry, they tend to prefer the positive j beta z, and there's some merit to that. But almost exclusively throughout electromagnetics, almost exclusively, it's minus j beta z. So there's some things to keep in mind. If you're in the minus j beta z convention over here, then you would express your complex dielectric constant as real minus the imaginary. Refractive index is real minus the imaginary. Whereas in the plus j beta z convention, there's pluses here. So depending on how you formulated your method, you might have to feed it slightly different material properties with changing the plus or minus to get it to work, if you're incorporating loss. And if you forget, it's not a big deal, because if you did it wrong and you looked at conservation of energy, so you send 100% of your energy in, you look at transmission and reflection, if you get 200% of your energy back, clearly whatever sign you used was gain. So you flip the sign and you get loss. So even if you forget, you can figure it out. So in this class, I'm going to show you one formulation with the plus j beta z, so you kind of get a feel of that. And then for the rest of the course, we're going to stick with the minus j beta z because it's probably the more dominant one out there. So we'll stick with that. But remember, it doesn't make a difference. And I've heard people argue over this of what's better. It doesn't matter. It's whatever. Okay, so here's a quick summary of what you'll need most of the time. So you're not going to be in this class struggling a lot going, oh, he gave me loss tangent and conductivity. Oh my, I'm not going to be doing that to you. I'm going to say the dielectric constant's 3, the wave's going this way, what happens? But anyway, all the information's here, just in case you're doing something and you're given a loss tangent, you kind of know what to do with it now. You have that information. So I don't need to go through this, but it's a table of dielectric constants and loss tangents just to give you a feel of typical numbers. So not much to say there. And then after that, a table of permeabilities. I should also mention your relative permeability and relative permittivity can't go less than 1. However, there are times where it can. I know that doesn't make any sense, but in this class, we're never going to let it go less than 1. But the short story is this whole mechanism of pooling charges, it's like a mass on a spring. It's a resonant phenomenon. And near the resonance, crazy things can happen where dielectric constants go less than 1 or even negative. But we tend not to operate near a strong resonance like that. So everything's going to be greater than 1 always. And also think of it this way, if it's less than 1, then all of a sudden your waves are going to travel faster than the speed of light, which isn't really possible, right? But it's been demonstrated. Okay. This is very useful to me for checking, but there's a duality between the electric fields and the magnetic fields. You'll notice like the curl equations look very similar, the divergence equations look very similar, and in fact there's a duality. So a lot of times what I'll do, if I'm formulating a method the first time, I'll derive an equation in terms of electric fields, and then I'll derive the same equation for the magnetic fields, and since there's a duality, they should match up. I should just replace E's and H's, B's and D's, and Mu's and Epsilons, and they should match up. And I do that all the time. If I get two different answers, clearly I made a mistake, and I whittle away at it until they match. So it's a great trick I've used all the time to get my formulations right. Okay. So here's what I think the most important part of this lecture. We're going to start with Maxwell's equations, and we're going to go step by step and prepare these things to be solved numerically. We're not going to solve them numerically today, but they'll be ready to. And so all the other numerical methods we talk about, we're going to start with this final set of equations that we're going to do today. So we will start with Maxwell's equations in differential form. We prefer the differential form because it's a little bit easier, although there is also merit to starting with them in integral form. And in time domain, because that's the most general. But in time domain, the ugly thing is we have these convolutions, and that's a real headache to manage. And there's also other benefits going to the frequency domain if it's a very resonant device or whatever. So the first thing we're going to do is Fourier transform Maxwell's equations to go from time to frequency. So I wouldn't say we're in Fourier space. That's when we Fourier transform x and y and z. So this is frequency domain, which is different than Fourier space. Does that make sense? So there's actually two different Fourier transforms we're eventually going to perform on Maxwell's equations. One Fourier transforms time, the other Fourier transforms space. But we're not going to Fourier transform space right now. We're only Fourier transforming time, so we go from time to frequency. And the cool thing that happens here is that we no longer have convolutions. We just have a very simple multiplication. But we still have 6 equations. We have Maxwell's equations and these constitutive relations. So the next very common thing to do is we'll take these constitutive relations and substitute them into Maxwell's equations to eliminate D and B. So we only have E and H left. And we could eliminate E and H and only have D and B left. But most often people leave E and H in the equations. So D and B are gone now, and constitutive relations are gone. And very often in the literature, you'll see these 4 equations. Ah, crud, I just changed slides and I can't go back. Anyway, you'll see those 4 equations, and they'll be called Maxwell's equations, even though they're not quite pure Maxwell's equations. They're Maxwell's equations with the constitutive relations substituted in. So the next thing we're going to do is assume our materials are isotropic. In the general case, our permittivity and permeabilities are tensors, which is a 3x3 matrix of scalar numbers. When they're isotropic, these off-diagonal terms all go to 0, and we'll have the same number going down the diagonal. So that's an isotropic material, and really, instead of writing this whole matrix thing, it just reduces to a single scalar. So we're going to do that too. We're not going to handle anisotropic materials in this class. There's some special things you have to do. So given that these are tensors, or I'm sorry, scalars and not tensors, we can then put them into Maxwell's equations, and Maxwell's equation reduces to that. Everybody good with that? So we start with Maxwell's equations, we Fourier transform into the frequency domain, substitute it in the constitutive relations, and then assume we have isotropic. We're ignoring anisotropic. And here we are. So everybody's good? What time is it getting to be? I'm not going over my limit, am I? Oh, we got plenty of time. Good. Okay. So now we have 4 Maxwell's equations. The next thing we want to do is expand them. Those are vector equations. So in fact, each vector equation represents 3 scalar equations, right? Or at least the curl equations. The divergence equations is just 1. So we have one of our divergence equations. We can expand out and write it this way. The other one we expand out right this way. And the important ones here are the curl equations. So this is a vector equation that becomes 3 separate scalar equations. They're coupled, and the other curl equation leads to 3 other equations. And what you'll see, for the most part, we're going to ignore the divergence equations. We'll touch them here and there. But for the most part, we're going to proceed with just these 6 equations, the curl equations. So now instead of having 2 vector equations, we have 6 coupled partial differential equations that are scalar. Everybody good with that? Another thing we're going to do is start to normalize everything. So back to the curl equations, and we keep mentioning the electric and magnetic fields are related through the impedance. They're 3 orders of magnitude different. Clearly that's something needs to be done there. So what is typically done, or what I like to do, is normalize the magnetic field using this crazy normalization. So this H, with just the arrow over it, that is the normal H field. We're going to multiply it by this square root thing to take care of the magnitude problem. By doing that, E and H will be the same order of magnitude. The other thing I like to do, which is a little bit less common to see, is include in the normalization a minus J. And what's really cool there, notice up here we have this J omega, another J omega. One has a minus, the other doesn't, and I can never remember which one has the minus. If we normalize the magnetic field this way, suddenly the curl equation is reduced to these 2 simple forms. They're both positive. The J omegas disappear. We just have K naught. That's 2 pi over the wavelength. These are much, much nicer equations, and they're much more symmetric now. They're both positive. There's no ambiguity in sign. Much cleaner equations. So it wasn't necessary to put the minus J in there. It just made things much easier in my mind. So start with Maxwell's equations, Fourier transform to the time domain, substitute in the constitutive relations. We're only handling isotropic, and we normalize the magnetic field. So what I have now is this little squiggly over top of the H to remind us that's the normalized H. So if we ever want to know the real H, we have to denormalize it. Everybody good? Okay. So here's the final set of 6 equations from the curl equations, and that's the starting point for almost all computational electromagnetics. Not everything, but that'll be the starting point for us, for a lot of things. So a lot went into that to get here. And everybody good and followed all that? You're laughing? Remember, there's no tests here, right? So you don't have to remember it. But what I want you to, given those equations, I want you to remember that there are some steps to get there. You know, we normalized things, we assumed isotropic, we got rid of the anisotropic stuff. So that's where we'll start. Everybody good? Okay. So we're going to talk a little bit about the wave equation because it's going to give us a little bit more intuitive feel of what's going on and foreshadow some things. And there's some useful conclusions from this that I apply all the time. So we said that the 2 curl equations is really what predicts propagation. Time-changing E leads to a time-changing H. Time-changing H leads to a time-changing E, and so on. So we get a wave. So it makes sense if we take those 2 equations and substitute them into each other, we'll get a wave equation, right? So that's exactly what we do. What I like to do is take the first equation and solve it for H, and then take this expression for H and substitute it in up here. And if we turn the crank on the math, this is where we end up. And that is a fully generalized wave equation. Mu and epsilon can change with position. Those are permittivity and permeability can change with position. So it's a very general wave equation. That's actually what we're going to solve. It's probably not a form you've seen before because you probably would have made the assumption that you're inside a homogeneous material. So this is not a function of position, so it can come to the outside of the curl operation. And when that happens, there's actually a lot more you can do to that equation to simplify it down. But real devices are not homogeneous. We can't control waves with homogeneous materials. There has to be interfaces and changes in the dielectric constant and curves and surfaces, right? Or we can't control waves. So nothing real is homogeneous. So this is really, in this class, as far as we can go. And we could do it one of two ways. We could derive a wave equation for E or a wave equation for H. And sometimes there's benefits or drawbacks doing it either way. But the point is, once we're here, we can't simplify this. But okay, so let's pretend now we're in a homogeneous material. We can bring the parameters to the outside, and we end up, if we turn the math crank, we end up with wave equations that probably look more familiar if you've had any kind of electromagnetics. So those look much more familiar. But in order to get there, we had to be in a homogeneous material. So it's this infinite material goes out to infinity, and it's all the same everywhere. Very boring. But that's the only way we can get that equation to reduce to this. Okay, so that wave equation is really just a second order differential equation which has complex exponentials as solutions. So that means we get waves from it. That's good, we get waves from our wave equation. So this is the general way to write the form of a plane wave. So your electric field as a function of position r, so r is a vector with x, y, and z, has some amplitude, which is also a vector, and then this phase term. So the way to interpret that is the k vector is the direction of the wave, that E naught is the amplitude. So the electric field is pointing off in some direction that's pretty close to perpendicular to that. So the wave's trucking along, but the E field's just oscillating this way, in the direction of E naught. And the H is the same way, same wave trucking along, and it has the H pointing in some other different direction. And it's just oscillating as the wave's propagating. We need to know that because if we're formulating a rigorous solution to Maxwell's equations, we're going to have to define a source. We're going to have to make the source a rigorous solution to Maxwell's equations, or it's all going to fall apart. So this is a rigorous solution, so this is how we do our sources. We already talked about the sign convention.
Is there a mistake on there?
Uh-oh, what's the mistake?
It looks like they're both plus, traveling in the plus x.
Ah, but I put a Z there. Yeah, right. Okay, good catch.
Well, A, it's C, and B, there's a sign issue.
Okay, so let's fix this. So this is a wave traveling in the positive Z direction, so that needs to be a Z. Anything else crazy? Everything else looks okay on that, at least sign convention 1.
The sign convention 2, I think.
Same thing, so that should be
Minus Z.
yeah. That's still, no, that's a positive
Oh,
Z
that
there.
is positive Z.
Yeah, because we're always talking about a wave traveling in the positive Z direction. It's just in this sign convention we put a minus, in this sign convention we have a positive. And the real key difference is how we express refractive index and dielectric constant. In this minus world, we need minuses here and here. So it's just something to keep in mind. And the little equation on the right is why that is.
Okay, also in the notes on the oscillatory terms.
Yep, okay. I don't know how I missed that. Yeah, so that should be plus Z, and this should also be plus Z. Thank you for catching that too. Wonder how many times I looked at that and didn't see it. Okay, so everybody comfortable with that? Okay, in some methods, we have to give it what the electric and magnetic field is. But when we have a wave, they're coupled. So we can't arbitrarily choose E and H. We can arbitrarily choose one, but then the other is fixed. So we need to know how to calculate that. So the way we do it is we take a general expression for one of them, we substitute that into one of the curl equations and calculate the other. That's really all there is to it. So given this electric field, this is how we would calculate the polarization of the magnetic field. K is the direction of the wave cross-producted with the amplitude of the electric field divided by a constant. And we can also write it this way if we do a little bit of math on it. So the way to think about it, K is the direction of the wave, E is going to be perpendicular to that, and then H is going to be perpendicular to that again. So EH and the direction the wave is going are all at 90 degrees with respect to each other. So with that equation, we can calculate H from E. And we may need to do that when we do sources. Is everybody good with that? Okay. Another thing, when we talk about this concept of a plane waves don't exist because plane waves are of infinite extent, which clearly is not real. And also plane waves have existed for all time. So they were there at the time of the Big Bang, and they'll be there billions of years from now when the universe does a big crunch or big whatever it does. So the point is, it's of infinite extent, it's always there. Plane waves don't exist. So when we draw a plane wave, a lot of times we'll just draw a little arrow. And it's easy to think that because we just drew a little arrow that it's somehow confined there. And it's actually not the case. We're talking about a phenomenon that exists over everywhere. So that's important to keep in mind with a plane wave. Anyway, that's about all. Any questions on that? I guess that reminds me of what I wanted to say about Fourier transforms. So suppose I told you I have this beautiful song. There's 587 A notes, 400 B notes, 300 C notes. Isn't that beautiful? Well, you know, I might be talking about one of Beethoven's symphonies, which is a beautiful song, but if I just tell you that, that's when you Fourier transform something, that's what's happening. You just know how much of each frequency is there, and the information about when it is there is gone. So when you analyze things in the frequency domain, this is also why it's difficult to do transient analysis in the frequency domain. You just lose that information. But it does simplify a lot of things. Your convolutions become multiplications. So there's a neat article out on the internet. If you go to Google and you type in dogma of the circle, it talks about that. And it talks about how science was held back and polluted just with this sense of a circle. And it actually comes from a long ago where people were very religious and God made the universe perfect and circles are perfect. Everything's a circle. And they were looking at planets orbiting. And they said, well, that's got to be a circle because that's perfect. And that did not fit the data. So then they said, all right, well, maybe it's the sum of two circles. So you not only have this planet going in a circle, but it's going in a circle on that circle, which is the concept of phasors, right? You started to add phasors. That didn't quite fit the data. And even though they were way back then, they had like 30 some of these little circles all superimposed until they finally kind of matched the data they were observing from the planets. And then, who was it? Newton, Galileo? I don't know. Somebody said, no, it's an ellipse, guys. And anyway. So think about that when you analyze things in the frequency domain. You now have these blinders on, and you lose all sense of time, which is unfortunate. All right, I don't know what put me on that, but off we go. Okay, so we have this, I can't go back, rats. So we have this differential equation, second order minus some term equals 0, right? And so now we want to know scattering from an object. We got a sphere, and we have this differential equation describing the fields. Turns out we can't do anything with that. We can't get a solution from that because we haven't told it what kind of wave we're hitting it with, right? Because that could change everything. So this differential equation equals 0 has to become something else. It has to be differential equation equals something that's not 0 that describes the source in some way. And the unfortunate thing, it's not real straightforward how to get this nice simple plane wave source into the form of that differential equation. I boiled it down to something pretty simple, but you can't just look at this term G and say, oh, okay, clearly that's a plane wave source coming in from this angle. It's a bit more abstract than that. But the point is we need a source to solve a scattering problem. So scattering being you have an object, you hit it with a wave, and it bounces, and we calculate what bounces, what scatters from it. So we need a source for that, or it's not solvable. Another way we could solve this, where we can leave it equal to 0, we solve it as what's called an eigenvalue problem. And eigenvalues problems arise where there is no real source, but there's, for whatever reason, a whole bunch of discrete answers. If you've ever studied waveguides, there's multiple modes that can exist in a waveguide. So you'll be solving Maxwell's equations there as an eigenvalue problem. There's no source, you're just asking what modes can exist here. And in fact, there's an infinite number of modes. And so in that case, you would solve it as an eigenvalue problem. No source is needed. So no source, you're probably doing an eigenvalue problem. An infinite set of solutions exist. If there is a source, there's only one answer. So, and do we do any eigenvalue? We're definitely going to talk about it. I don't think I have you solve anything as an eigenvalue problem. But, so does that make sense? Scattering problem, you hit it with a wave, clearly there can only be one answer. Otherwise, every time you go in the lab and you hit the object with a wave, something different's going to happen. And that makes it impossible to design anything. So that doesn't happen. You hit it with the same wave, the same thing happens each time. So one answer for a scattering problem, you give it a source. Eigenvalue problems, you're looking for multiple answers, and there is no source. You're just saying what modes could exist here. It doesn't tell you what modes do exist. It's just going to tell you what modes could exist. And so here I'm showing some modes in a waveguide. But I could go in and selectively only excite one of those. So again, the eigenvalue problem doesn't tell you what actually exists. It just tells you all the possibilities, and it's up to you to selectively excite one over the other if you wanted to. Okay, wave equation versus Maxwell's equations. Maxwell's equations has the full rigor. We take the two curl equations, we substitute them into each other, and we get a wave equation. The problem is when we've done that, we've eliminated a little bit of information, and it turns out a lot of methods can run into what's called spurious solutions. So in other words, you solve it, and the answer you get is completely wrong, doesn't make any sense. You'll get 800% reflection from an interface that's absolutely impossible. It can't reflect more than 100%. So what we tend to do is we back up to Maxwell's equations, that set of 6, and we fix the problem that causes the spurious solution there. Once we've fixed the problem, then we substitute one of the curl equations together and get this new wave equation, but the problem's been fixed. So we always start with Maxwell's equations, not the wave equation, because of that, because there's problems that happen that we fixed earlier on. Does that make sense? And you'll see that when we get into it.
Are those problems readily apparent?
Yeah, so, okay, the quick answer there if you're curious. So we're going to develop our codes based on the curl equations, and we're going to kind of ignore the divergence equations, at least in terms of our equations. So we're not enforcing the divergence equations. And what will happen for some polarizations, if you have an interface between two materials, you'll hit it with a wave, and because we're not enforcing zero divergence, it's going to create divergence. And it's going to be like these little tiny sources at the interface between materials that actually add energy to your model or take it away, and all kinds of craziness happens. So what we do is we modify Maxwell's equations consistent with the divergence equations, and that'll make more sense when we get to it, but it fixes that, and now we don't get that problem. And we don't get these, they're called spurious solutions. And it's usually due to not enforcing the zero divergence. So that's a quick answer. All right, everybody good? 3 hours is a long lecture, isn't it? Okay, so the last part of this lecture before we jump into MATLAB. So there is no fundamental length scale in Maxwell's equations. If you have any semiconductor background, the equivalent to this is Schrodinger's equation. It turns out there is a fundamental length scale there, but there is not in Maxwell's equations. Now that's very cool, because if, let's say we have an antenna and it works wonderful at 1 gigahertz, does exactly what we want it to, but we actually want it to work at 5 gigahertz. Do we throw out the design and start all over? It turns out if we want to go from 1 to 5 gigahertz, we take every physical dimension and scale it down by a factor of 5. Now it's going to work the exact same way at 5 gigahertz. because there is no fundamental length scale of Maxwell's equation, we can scale. So if you see a good design you really like, but it's not at the frequency you like, doesn't matter. Then you just scale it. You make it bigger or smaller, and you can get any design to work anywhere. So for that reason, we usually just normalize the length in Maxwell's equations, and we'll just call the size of our antenna 1. Well, 1 what? 1 whatever you want it to be. 1 meter, 1 centimeter, whatever you want it to be. Because of the scalability. So that's really, really useful, and we use that all the time. So here's the sort of proof of that. So we start off with our wave equation, right? Then what we're going to do is we're going to scale it. Everywhere there's a physical dimension, we're going to scale it by A. So if A is greater than 1, we're stretching the thing. If it's less than 1, we're going to compress. So everywhere there's a dimension, R, that's a position, we'll divide by A. This gradient operator is a spatial derivative. We're dividing by a spatial dimension. So here we'll multiply by A. So all we're doing is scaling the physical dimensions by a constant A. Now what we can do is pull A out and bring it under the frequency term. So what we have is the standard wave equation again, but just with the frequency scaled. So in other words, the device is going to do the exact same thing, the scaled device, just at a different frequency. So that's kind of proof of that. That's really, really useful. Another thing we can do is scale the permittivity and permeability. And if we double the permittivity everywhere, it's going to not halve everything. It's going to go down by 1 over square root of 2. So we can scale either or both. Now the problem with scaling is if we move to a different frequency, very often the dielectric constant is going to be different at a different frequency, so this isn't exact, but at least in principle this does work. You just have to take into account your new material properties at the new frequency. So the scaling is really important, very, very useful. I think that's it for the slides. Any questions? Is that the last slide? Because I can't go backward. Any questions on this? What time it is? We probably have time to jump into MATLAB. Yeah, we got 20 minutes. All right.